Hey everyone, welcome back to Everything is Relative. I'm Mr. K, and today we're going to be looking at topical questions on the topic of dynamics for Cambridge A-level physics, and specifically for paper 1, which is the multiple choice. Now we're going to be looking at questions 251 to 262, and I'll try to make videos on every one of the topics and then come back to the remainder of the questions. But this will be a good start when you're preparing for your paper 1 exam for A-level physics, to be working with as many past year questions as you can. And although paper 1 is only based on AS physics content, it can be quite tricky, and your 4 available options for multiple choice are usually very similar and usually represent common errors, common mistakes, and so it's very easy to make an error that you think might be correct and end up being wrong. So the first question is question 251. As you can see, it's from the March 2020 exam, from question paper 1 variant 2, and it's question 6 from the paper. And we are told that a stone is thrown horizontally from the top of a cliff and falls into the sea below. With air resistance being negligible, the path of the stone is shown, and we want to know in which direction the resultant force on the stone acts during its fall. Is it horizontally to the right, parallel to its velocity, perpendicular to its velocity, or vertically downwards? Now let's draw a free body diagram. Let's draw the diagram of the forces acting on the object. So the stone is thrown and there isn't any air resistance, and we know that when an object is, whether it's a projectile, whether it's in free fall, whether it's moving horizontally at some instant, if there's no air resistance, the only force that will be acting on the object is the weight of the object, and the weight will always be vertically downward towards the ground and towards the center of the earth. So that weight is the net force on the object. It's the net force, it's the only force, so the force on the stone will be vertically downwards. There will not be any other forces irrespective of how the object is moving, because in the horizontal direction there will be no force, and the vertical direction is only one. And so the object falls downward. And so that corresponds with option D. So don't doubt all the things that you already know about forces on objects in motion. There'll only be one force on this object, which is the weight acting vertically downward. The next question is 252. It says that a person of mass 60 kilograms stands on an accurate bathroom scale, placed on the floor of an elevator which operates in a tall building. At a certain instant, the bathroom scale reads 58 kilograms. Which row could give the person's direction of movement and the type of motion? So they give us different directions, is the elevator moving up or down, and they want to know if the motion is at constant speed or if the elevator is slowing down. It's decelerating. So let's choose the downward direction to be positive. Let's just use a convention. Doesn't really matter which direction we choose. So there's a person on an elevator, and there are two forces acting on this person. Their weight, which is equal to mg, vertically downward, and then the reading on the scale, which is the contact force that the scale applies on the person. So I'm looking at the forces on the person. We'll call this the normal force, the contact force between the scale and the person. And that normal force N is actually the reading on the scale. And so in this case, that reading on the scale will show 58 kgs times G. It'll multiply that value by G and give you a quote-unquote weight. And the weight will change if you're moving up or if you're moving down. But how does it change? Now, what we can see is that the normal force, which points upward, and the weight are going to be different, because the actual weight of the person is stationary. The scale would just read 60 kilograms. But since it's reading less than 60 kilograms, this person is moving. We need to figure out how this person is moving. Now, according to Newton's second law, the two forces are not going to be balanced here, because we can see that the normal force and the weight, which are the two forces acting on this person, are not balanced because they should be reading 60, but they're reading 58. So one force, let's say N minus the other force W, must equal to ma. This is Newton's second law. Okay, so immediately we can see that the speed of this person is not going to be constant. So we can eliminate A and C. We still have B and D though. Now, is the person moving upward or are they moving downward? But we can also write this N minus mg equal to ma. And what we can see is that N is smaller than W because the reading on the scale is less than the weight. So N minus mg is a negative number since N is smaller than the weight. If N minus mg is 0, then by the convention we've used where downward is positive, any negative value is going to be upward, which means the value for ma is negative, meaning the value for the acceleration a is negative. Mass cannot be negative. If a is negative, then a is upward. So this means that the acceleration, the direction of the acceleration is upward. And so what that does is it leaves us with only option D, that the elevator is accelerating upwards, and the fact that it's slowing down means it's accelerating or decelerating. So it is undergoing acceleration, it's slowing down, and it's moving upwards. So whenever you're faced with an elevator problem, always try to resolve the forces acting on the individual on the scale in the elevator. We usually add a scale in the elevator to measure the contact force on the individual. So that was question 252. The next question is 253 from the summer 2020 exam. That's May, June 2020, question paper 1, variant 1. It's question 8 from that paper. And we're told that a car accelerates from rest in a straight line with constant acceleration. And we want to know which graph best represents the variation of the momentum P with the car with the distance s traveled by the car. Okay, so I'm just going to erase the previous question. Now we're asked for the momentum, the variation of the momentum with the distance, not with time. Because if you want to find the variation of momentum with time, it's very easy to see that one of these graphs would be correct, but it's correct for a different problem. So what I would do for this problem is I'm trying to express the momentum in terms of the displacement. So the first thing I'm going to do is write an equation of motion. It starts from rest, and after some time it has a velocity v. V squared equal to u squared plus 2as. Now I use this equation because we have constant acceleration. So for uniform acceleration, we can use the kinematic equations of motion, any one of them. And I like this equation because it's got acceleration, distance, speed, and initial velocity as well. Initial velocity is 0, so v squared is simply 2as, which means that the speed v is the square root of 2as. So the speed v is related to the square root of the displacement. So as the displacement increases, v increases, but in correspondence with the square root of s. And what do we know about the momentum? Well, the momentum is simply m times v, which is, I'm going to write m as the square root of m squared so that I can put everything under the square root sign. And I get p equal to mv is equal to the square root of 2m squared as. Where m and a are both constants, 2 is obviously a constant as well. So the momentum varies with the square root of s. Since m and a, I'll just write that down, m and a are both constants. They're not changing with time. And so what this means is that the momentum is proportional to the square root of s. So I'm plotting a graph of p against s, so I'm getting a square root graph. It's basically a graph of y against the square root of x. Y equals to the square root of x, and this corresponds with graph A. So if you know your mathematics, you know that the square root graph has a shape where it's steep initially and then sort of flattens out afterwards. So it's not one of those immediate obvious graphs that we know of. We have to use the relationships that we know in order to create a relationship that we don't know. And so a little bit of a tricky question there and requires some mathematical manipulation. The next question is number 254 from the summer 2020 exam, question paper 1, variant 1, and it's question 11 from that paper. We are told that a wooden block rests on the rough surface of a board. One end of the board is then raised until the block slides down the board at constant velocity v. And we want to know which of the statements describes the forces acting on the block when it is sliding with constant velocity. Frictional force and the resultant force. We basically want the direction of the frictional force and the resultant force. And for a problem like this, what we would do is we would draw a free body diagram and try to count all the forces that are acting on the object. So because the plane of motion has been tilted, I'm going to tilt my entire axis in the same way. And I'm going to think of the axes as parallel to the plane and perpendicular to the plane. Now, parallel to the plane, I have the weight of the block parallel but downward. I'm going to call it W parallel. That's the component of the weight that is parallel to the plane. And then in the opposite direction, I have the frictional force. It's a rough surface, so I'm going to call the frictional force little f. And obviously, since the block is moving at constant velocity, the parallel component of the weight is equal to f. Okay, and I can just make a note that this is constant velocity. But also I have to consider the other forces. So there's a component of the weight that acts perpendicular to the plane. And those two components of the weight, parallel and perpendicular component, must be 90 degrees. But the block is neither moving down through the plane or jumping up vertically off the plane, relative to the plane or normal to the plane. So the normal contact force, we can call it N, must be equal and opposite to the weight of the block, since it's not moving perpendicular to the plane at all. So that means that the perpendicular component of the weight must equal the normal reaction force, which is always normal to the surface, which is tilted. And this is because, and I'm going to write it down, there's no movement perpendicular to plane. So those two forces must balance as well. So what does this mean? This means that I've labeled all the forces, and there are no resultant forces, so there's no net force on the block. So the resultant force must be 0, so we're left with B and D, but the frictional force must act up the board, which has to be option D. Frictional always oppose the motion. Block moves down, so friction will point up. No net force, so the option D is the correct answer. Question 255 says the resultant force acting on an object is slowly increased. Which graph would show the variation with time of the momentum of the object? Okay, another tricky one because we don't really know what momentum against time would look like for an object where the force is slowly increasing. So now they told us that the resultant force on the object is slowly increased, and we want to know the variation with time of the momentum. But remember, this object could have some momentum, and then the resultant force could increase in the opposite direction to the momentum, meaning it's going to decelerate. It's not necessary that option D or option A is going to be the correct answer. It could be that the object is slowing down because the resultant force is opposing the motion. So in this kind of question, I'm going to say that the magnitude of the net force is equal to the rate at which the momentum is changing, at least in magnitude. So it could be increasing, it could be decreasing. Okay, but what this will do is give me some constant increase with time. It's increasing with time because as I get further along in time, the force is increasing, and so the rate at which the momentum is increasing also increases. And it's saying that they're slowly increasing it, so it's increasing in increments. So there's some constant increasing with time. It's not a sudden increase, a stop, and then another slower increase. It's a constant increase with time. I can also think of it, I don't have to, but I can think of it as the final momentum minus the initial momentum is F times T, if I were to write it in mathematical form. Because delta P is final minus initial, the force at any time is F, and the time, obviously, we'll call it T. So at any point, the final momentum is equal to the initial momentum plus the force times the time, the impulse, if you will. And the thing with this equation is F is changing with T, so F is not constant here. If F were constant, then this would be a nice straight line graph. But F is changing with every value of T, F is changing. So this is some constant value, P initial, plus a bigger value every time time is increasing. So what this means is, since F is changing with time, the gradient of the line is not constant. So it immediately eliminates option D, not constant gradient. You don't really need this point because option D is only one of the four. But if you want to eliminate something, we can eliminate option D. So now that I know there's some constant increase with time, or there's at least an increase with time, the actual important point that I could have got from the first line is that the gradient must get steeper with time. That's actually what's important here. So the gradient must get steeper with time. And I noticed that that's not true for A, C, or D. With A, the gradient gets shallower with time. With C, the gradient also gets shallower with time. We don't know if it's an increase or decrease, remember. But what we do know is that as time gets greater, the gradient of P against T increases only for B. The magnitude of the gradient, what I should say is the magnitude of gradient gets steeper with time, or gets, well, greater with time. So you don't have to use, because steeper could be plus or minus. And so the only option there is B. As time gets increases, then the force increases. So the rate at which the momentum is increasing or decreasing gets greater. And so the gradient must get steeper. And you can see that's the only one that sort of stands out in this problem. Just looking at the graphs might be a bit difficult to come to that conclusion, but doing this mathematical understanding means with just one line you can understand, okay, force is gradient of P versus T. As force increases, the rate at which the momentum is changing must change as well. And so that can only be option B. The next question is 256. It's from summer 2020, question paper 1, variant 3, and it's question 8 from that paper. We are told that a ball of mass m travels vertically downwards and then hits a horizontal floor at speed u. It rebounds vertically upwards at speed v, and the collision lasts a time delta t. What is the average resultant force exerted on the ball during the collision? So let's actually draw the three scenarios here. So here's the ball just before it collides with the floor. It's moving downward with a speed u as a mass m. We'll just label this before the collision. Then it collides with the floor for a time delta t, still mass m, and the force that acts on the ball during this time, we'll call it F. We'll say this is during the collision. And then after the collision, we know that it starts to move upward. Mass m, final velocity v. And we know that momentum must be conserved. Now the average force, in magnitude at least, is delta p by delta t. Now the reason why I'm pointing the force upward is because the object is initially moving downward and its final motion is upward. So the force must point in the direction of that final motion because it's changing the speed from a negative value to a positive value. So the force must be applied upward in the ball as the ball applies a downward force on the wall. And so this is mv, the final velocity, minus now the initial momentum, so minus m. Now the initial momentum is the opposite to the direction of the final momentum, so there must be a minus sign there because it's a vector. It's pointing in the opposite direction, so it must be minus u. In magnitude, we have to write down the minus sign, divided by the change in time delta t. And that's because u and v are in opposite directions. And so what this means is that delta p by delta t is mv plus mu over delta t. If you've already done A-level physics, you would have seen this for the ideal gas derivation. But the average force, which is the rate of change of momentum by definition, is mv plus mu over delta t, and this force acts upwards because the change in momentum is upward, so the resultant force must be upward. And so this corresponds with option D. So just be very careful. If the velocities are in different direction, then we have to account for the direction in one of our symbols. So in magnitude, it'll be mv plus mu over delta t. So the next question is 257. It's from summer 2019 exam, question paper 1, variant 1, and it's question 9 from that paper. And it says each diagram illustrates a pair of forces of equal magnitude. Which diagram gives an example of a pair of forces that is described by Newton's third law of motion? Okay, so again, let me just erase all of this. So we have to first tell or remind ourselves at least what Newton's third law says. Let's take an example of Newton's third law to describe it fully. So Newton's third law says that if an object A exerts a force on object B, then B will exert a force that is equal in magnitude on A and the opposite direction. So if we know the Newton's third law, we must have two objects. So I'm going to take an example of a ball striking a wall. The ball's moving to the right when it hits the wall. And so if I draw the free body diagram, what I have is that there's a force that the wall exerts on the ball. We'll call it F1, and that one points to the left. But most importantly, it's on the ball. That's the action force. The reaction force cannot act on the ball as well, because Newton's third law says that the reaction force must act on the second object. So if the first force acts on the ball, the second force must act on the wall. That's the force that the ball exerts on the wall. These two are equal in magnitude, but they're opposite in direction, and they act on two separate objects. So the most important thing there is that we have two objects. For A, for C, and for D, we only have one object. The car in A, the box in C, and the plane in D. Option B is the only one where there are two objects. The Earth exerts a force on the moon, and so the moon exerts an equal and opposite force on the Earth. And so the only correct option there is option B. So be very careful. Just because forces balance doesn't mean that they are an action-reaction pair. In fact, an action-reaction pair should be on two different objects, not on the same object. So just be wary of those kinds of questions. The next one is question 258. This is from the summer 19 exam, question paper 1, variant 2, and it's question 9 from that paper. And we asked, what describes the mass of an object? Well, we should know this, because we should know what the definition of mass is. Is it the force that the object experiences due to gravity, the momentum of the object before a collision, the resistance of the object to changes in motion, or the weight of the object as measured by a balance? Well, How can any of those be mass if they give us a different quantity? If I ask you what an apple is, but if I give you options as orange and pear and banana, immediately you know one thing cannot be another thing. But either way, let's write down an equation for Newton's second law. F is equal to ma. And the acceleration of an object, the change in an object's motion, is F over m. What this means is if I have a greater mass, then I have a lower acceleration. Aha, so the change in motion is hindered by the mass of an object. In fact, greater mass, lower acceleration. So option C looks the most promising because what this means is the more mass I have, the more I will resist any changes in motion. The more I'll resist having a high acceleration. So by definition, we say that mass is an object's sort of inertia. It's property that allows it to resist motion. The greater the mass, the more it will resist being accelerated by a resultant force. Okay. So that one, you don't really have to do any writing. So if you see me doing writing, there's no necessity for you to do writing. But if you feel like you need to convince yourself, or if you need to do a calculation, then by all means do your calculations aside. Put a circle on the answer sheet before you even, or on the question paper rather, before you even go to the answer sheet, because later on you may want to change an answer and it might be too late. But the next question is 259. It's from summer 2019, question paper 1, variant 2, and question 10 from that paper. We're told that a car has a mass m and a person needs to push the car with the force F in order to give the car acceleration A. The person then needs to push the car with a force 2F in order to give the car an acceleration 3A. We want to know which expression gives the constant resistive force opposing the motion of the car. Okay, so again, we can simply draw a free body diagram or a force diagram, or even just a fully labeled diagram like what I'm going to do here. So this is, believe it or not, this is a person pushing what I think is a car. And the applied force, F, is to the right in my case. And there's a constant friction force. They did mention that this friction force is constant in the opposite direction. I'll give it the symbol little f. So with this first piece of information, I push the car with a constant force, big F. There's a constant resistive force, little f, acting in the opposite direction. And this must equal ma, because the mass of the car is a and the acceleration is a, as they've told us. But this doesn't help me solve for little f, because what I want to do is actually solve for little f. What I then see is that I apply a force of 2f, and I still have a constant opposing force of little f, and this is equal to 3ma, since the acceleration is now 3a. And I can call this equation 2. Now I have a system of two equations, and I need to eliminate big F, so I'm only left with little f in terms of m and a. So what I can do is take equation 2 and subtract 2 times equation 1. And what I get is that little f, the resistive force that I want, is equal to ma. But if you do the mathematics, you see little f is equal to ma, and this corresponds to option A. And so again, a question like this, if you're given multiple pieces of information, mathematically usually requires a system of equations to be done. So you need to set up 2 or more equations, which means that you then have to do some simultaneous equation solving to find one thing in terms of the other things. Okay, so not too bad, but quite mathematical in nature. The next question is question 260. It's from summer 2019. It's question paper 1, variant 2, and it's question 14 from that paper. Okay, we have a car of mass m traveling at constant speed up a slope at an angle theta to the horizontal, as shown in the diagram. Air resistance and friction provide a resistive force of F, and the acceleration of free fall is g. Okay, so we basically want to know the force that is needed to propel the car at this constant speed. Remember what we know about constant speed. Constant speed simply tells us that there's no net force acting on the object. It doesn't mean that there aren't any forces. So I'm going to draw my free body diagram like I always seem to be doing. I have a driving force acting up the slope. I'm going to call the driving force R, since I can't use F. So this is the force that is pushing the car up the slope, acting against the air resistance and friction. The friction acts directly opposite to this, 180 degrees opposite to this, and the friction force is big F. Are there any other forces acting on the car? Yes, well, its weight is acting vertically downward. But I tell you what, I'm going to break the weight into components because now I'm using a ramp that is at some angle. So I have the component of weight parallel to the plane, which you see I like to call W parallel. I often do that, at an angle theta to the horizontal. And I have a perpendicular component of the weight that acts perpendicular. Well, a component of the weight that is perpendicular to the inclined plane. And the car is neither moving down through the plane, nor is it moving up from the plane. So it's the force that is perpendicular to the plane must be balanced, must be a balanced force. And so if the perpendicular component of the weight is that way, then there must be some normal force that way. So what I can tell from here is that obviously the perpendicular component of the force of the weight must equal the normal reaction force that the surface, the ramp is applying on the car. But what I really care about is the forces that are parallel to the plane, because we want to know what R is. Basically, we want to calculate for R. So if I take this force diagram, and for the weights, I specifically, because F is constant, but I need to figure out what W parallel and what W perpendicular look like in terms of mg and theta. So if I have my weight vertically downward, then I will have the component of the weight that is perpendicular to the plane that way, and the component of the weight that is parallel to the plane that way. And between them, there must be an angle of 90 degrees because the two components must be at right angles to one another. And we said that the angle of W parallel with the horizontal is theta. But what this means is that I do a little bit of mathematics and I can see, just move this W, I can see that this angle here will also be theta. Okay, because the angle between W and W parallel will be 90 minus theta, and so the remaining angle between W and W perpendicular is theta. So with a little bit of geometry, I see that sine theta is W parallel divided by, so the component of the weight parallel to the plane divided by W, which means that W parallel is W sine theta, or mg sine theta. Aha! So therefore, we have that this driving force R, which they asked us for, must be equal to the two forces that are acting in the opposite direction to it, which is F plus W parallel, which is mg sine theta plus F, which is option D. So a little bit of mathematics was required for this problem. And the first thing you would always do is to draw a free body diagram. There's no net force in any direction, but always try to set your problem up so that you have two directions that are each perpendicular to one another. And then the rest of the problem becomes geometric in nature. So mg sine theta plus F. Again, you didn't need as much working as I had in terms of writing, but the logic will be the same. So I'm just trying to show you what the first principal basis would be in order to solve this problem. Now the last question we'll do for this video is question 262. We'll ignore question 261 because it was based on electric fields, which has now moved to A-level physics, so that's only in year 2. Question 262 is from the winter 2019 exam, so October, November 2019, question paper 1, variant 1, and it's question 6 from the paper. Now we are shown the velocity time graph for an object of mass 2.5 kilograms, and we want to find the resultant force acting on the object. And well, the velocity is given in meters per second and time in second, and we want to find the resultant force in newtons. So actually, this is not too bad. From a graph of velocity versus time, I can find acceleration. Acceleration is the rate of change of velocity, delta v by delta t. But the resultant force from Newton's second law is m times a, which is a constant mass m, times delta v by delta t, which is simple. I can just put my mass in 2.5 and find the gradient of this line. And so if I find the gradient of this line, that's 12 minus 3 meters per second divided by a change in time of 15 minus 0 seconds. And so what I should get is that the resultant force, F, is 1.5 newtons. So quite a relatively easy question considering the ones that we've done before, but this corresponds with option C. And so as you can see, some of the paper 1 questions rather, are quite tricky. They can require some conceptual understandings. You don't need to show as much working as I generally do, but I'm showing you how I would think about solving the problem. If you solve it without putting pen to paper, then great, it saves you time. If you need to put pen to paper, I suggest you do. And we'll do more of these questions for different topics before I come back to these topics again later on. But if this video was helpful, please leave a like, leave a comment, subscribe to the channel if you haven't already. But from me, Mr. K, that's all for now. I'll see you again next time on Everything is Relative.